Hello, folks. World is on fire. World is on fire. But we're going to talk about a Dutch PhD thesis. This is number something in a series that I'm doing about Eelco Dolstra's PhD thesis called The Purely Functional Software Deployment Model. We finished a chapter about the Nix language, chapter 4, and we're going to move on to chapter 5, the extensional model. And here we say the current and subsequent chapter formalize the operation of the Nix system. And chapter 5 and chapter 6 are different sort of implementations of the Nix system, I suppose. Chapter 5 describes what we all know and love, and chapter 6 is called the intentional model. And that is also, I think, called the content address store, which is being worked on, I think. It implements all the deployment properties described in chapter 2. It allows the intentional model described in chapter 6, allows the sharing of a Nix store between mutually untrusted users. But it places slightly stricter requirements on components. I guess we'll find out about that. But it says most of the aspects of the extensional model carry over without modification to the intentional model. So section 5.1, cryptographic hashes, sort of talk about what a cryptographic hash is. I won't belabor that. Nix initially used MD5, which produces 128-bit hashes, but it was cracked. And then they moved to SHA-1, 160-bit hash, and then that got cracked, and they moved to SHA-256. MD5 and SHA-1 are available in functions such as fetch URL for compatibility. MD5 hash of hello world, and if we get a base 16 representation of it, which is hexadecimal, we wind up with this string here. And there's also a print hash 32 that returns a base 32 string representation of a byte sequence. And its usefulness is that it's shorter than the sort of hexadecimal representation produced by print hash 16. It's a base 256 encoding of some number. Little Endian uses these digits, those digits, all the alphanumerics excepting E, O, U, and T. This is to reduce the possibility that the hash representation contain character sets that are potentially offensive to some users. Oh, that's funny. Okay. All right, whatever. Okay, so we have a print hash 32 of a SHA-1. It comes out to something like that. And I think this is actually 32 bytes. It is sometimes necessary to truncate a hash to a specific number of bytes. For below, we will truncate the 32-byte SHA-256 hashes to 20 bytes. 20 bytes, huh? How many bytes? Is that 160 bits? You're not gonna. Yeah, 160 bits. Oh, God. 32. How many bytes is this? Uh, 32. So that's 100. Oh, yeah, SHA-1. Okay. Okay, that's fine. Sure. Yeah, so he says it's sometimes necessary to truncate a hash to a specific number of bytes. For instance, below, we will truncate 32-byte SHA-256 hashes to 20 bytes. Of course, this reduces the security of the hash. So when he says it's sometimes necessary, what he means is it's always necessary as far as Nix is concerned. Representation it gets back from SHA-256, the byte stream it gets back from 32 bytes to 20 bytes in order to form 160 bits, which then get translated to 32 bytes of ASCII data, forming the printable hash. Got it? Yeah. Yeah, good times, good times. All right. The Nix store is a directory in the file system that contains file system objects, such as files and directories. In the context of the Nix store, FSOs typically represent software components, user environment, store derivations. All modern operating systems have, at the very least, have hierarchical directories of files. Beyond that, there are many extensions. We have symlinks, permissions, attributes, streams, multiple roots, hard links, device nodes. It says, fortunately for our purposes, most of these features are not relevant, can be ignored. Some, such as permissions, we would ignore to make life simpler. And we absolutely cannot ignore for deployment of Unix software is files, directories, and symlinks. While we can get away with disregarding most file permissions, the executable bit must be maintained. This leads to the grammar for FSO shown in Figure 5.1. So an FSO is a regular FSO is an executable. It's got a executable bit and it's got a byte stream. A directory FSO is a sequence of those, and a symlink is just a byte stream. It has no executable bit. Okay, we go over what a directory is. I think we all know what that is. We do not keep any meta information about files other than the executable bit. Notably, timestamps are discarded. So in the next store, nothing has a timestamp. To perform operations on FSOs such as computing cryptographic hashes, scanning for references, and so on, it's useful to be able to serialize FSOs into byte sequences, which can then be deserialized back into FSOs. So I guess, yeah. Okay, so an output derivation is turned into one of these serializations in order to compute its cryptographic hash. I didn't know that. I thought maybe I just walked the tree. Cool. Says that we have some examples of zip and tar, but these have two problems. They don't have a canonical serialization. Given an FSO, there can be many different serializations. Tar files can have variable amounts of padding between archive members. Okay. And this is bad. Don't do that. They store more information than we have in our notion of FSOs, such as timestamps. This calls FSOs that Nix should consider equal to hash of different values, just because the dates differ. Okay. Tar format is the only truly universal format in the Unix environment. It has many problems, such as an inability to deal with long file names and files larger than 2 to the 33rd bytes. Okay. Nix has its own, for these reasons, Nix has its very own archive format, the NAR format, Nix archive format. And I guess it just sorts the lists of entries in a directory by name, comparing the byte sequences of the names lexicographically. Okay, so I guess the intent is to provide something that can be hashed. So those are what NAR files are. They're like tars, except they always serialize to the same byte stream. Store paths 522. A store object is a top-level file system object in the Nix store. It is a direct child of the Nix store directory. Indirect subdirectories of the Nix store are not store objects, but contained in FSOs that are store objects. A store path is the full path of a store object. It has the following anatomy: store dir /hash part -name. The first part is the path of the Nix store, denoted store dir. The second is a 160-bit cryptographic hash in base 32 representation. And then finally, there's a symbolic name intended for human consumption. So here we have an example. We got the store path. We got the hash here. We got a dash. Then we have the symbolic name. Yeah, so here's some pseudocode for deriving a NAR. On the other hand, this, which is the store path plus /bin/hello, is not a store path, but has a prefix that is a store path. Usually, store dir is a Nix store, and this thesis will tacitly assume that it is. For binary deployment purposes, it's important that Nix store locations on the source and the target machines match, and we'll see why in a second. Symbolic name is alphanumeric, ASCII, some subset of characters. Store paths are always fully canonicalized. They don't have dots or slashes. extra slashes in them. No component of the store location stored there is allowed to be a symbolic link. So this means that neither /nix nor /nix/store can be a symlink. How do we compute hash part of store paths? The Nix store path and the symbolic name are part of the hash. That's pretty neat. This means that Nix stores in different locations yield different hash parts, and sources or outputs that are identical except for their symbolic names have different hash parts. Really interesting. Okay. Different types of store objects, notably sources and outputs, have different hashes. This prevents users from adding sources that impersonate outputs. Interesting. Okay. Not a major issue, but is important for security in a shared store that uses technique described in section 6.2. Okay, so this is future proofing for the intentional model. These properties achieved in the function makePath, which computes store paths as follows. So we have makePath, and then okay, so S is type, which is either store or source or output, I guess, something like that, plus colon hash name colon plus description. I don't know what that is. No, it's the hash. Oh, duh. Yeah, it's the hash. Okay. Okay, yeah, that's fine. Of course it's the hash. What else would it be? Okay, so why do we truncate the SHA-256 hash to 160 bits? Well, Nix originally used base 16 hexadecimal representations, 128-bit MD5 hashes, giving 32 characters. And then MD5 got broken, then 160-bit SHA hashes. And hexadecimal representation was that time replaced with a base 32 representation, which was also 32 characters. But then SHA-1 got broken, and they started to use SHA-256. Unfortunately, hash parts are too long, 52 characters. Together with the symbolic name, they exceed the maximum file lengths of some file systems, particular CD-ROM stuff. For this reason, the SHA-256 hash is truncated to 160 bits, and that's what he was mentioning up here when he gave this little thing here. It is sometimes necessary. It is always necessary. The assumption is no less secure than 168-bit SHA-1 hash, and possibly more secure. I don't know. It sounds a little suspect to me. But I'm no cryptographer. I don't think he is either, though. I don't know. Whatever, man. Random shit. So 523, path validity and the closure invariant. Metadata that's stored in a separate data structure about the Nix store in a number of database tables. A set of valid paths, which are finished. Those contents will no longer change. So, everything in the store is immutable, and if it is finished, it means that there are no more changes will ever be made to it. Output path of a derivation isn't marked as valid until the builder of the process that produces it finishes successfully. Contents of an invalid path are undefined, except when it's under construction, in which case a lock is used to indicate this fact, okay? There's a references graph, like for each path. Store path found, there are references to other store paths. This is discovered by scanning. The substitutes have been registered. These are the caches that can be used to get the binary representation. Traceability information for each valid output path. Nix remembers the derivation that built it. So the source derivation. What is it called? Source derivation. Store derivation. Store derivation. Yeah. The current Nix implementation stores this information in a transactional Berkeley DB database. I think this might not be true anymore. I think I've seen some SQLite errors. I think this is now SQLite. And this makes sense. Like this is 2006. And back in the day, the first thing you would reach for is you need a transactional database that you didn't want to pull on, Postgres or something else. You typically reach for Berkeley DB because it was embeddable. These days, I think, it's the 2006 equivalent of SQLite, which I think we use now. Transactions are important. Yes, they are. Yeah, we have a mapping of path to hash, and that all the stuff that's in that mapping is called valid. It means that these things really are valid as far as Nix is concerned. What's on disk can be checked against it, I presume. And the path is valid. It exists in the Nix store. When the path is made valid, the valid entry for the path is set as follows. So valid P equals SHA-256 : and then the hash. 32-byte representation. The name of the hash algorithm is incorporated to facilitate future operating hash algorithm. Okay, so saying the purpose of storing the hashes is to detect tampering. So you could imagine a valid table that was only just, you can just imagine a sequence of paths that were the valid paths, but maps the path to its content hash in order to be able to verify it later. Consistency. Okay, stored hash invariant. The contents of valid stored paths correspond to the cryptographic hash stored in the valid table. There's a references mapping, which maps a path to a set of paths, and a set of store paths referenced by each store object. Sources, references are usually empty. Store derivations are exactly the union of the store paths listed in its input sources and input derivations fields. And for output paths, actual derivations, they are found through scanning using the method outlined in section 3.4. It's acyclic, except for trivial cycles defined by self-references. Okay. Important property of the Nix store is that all times the following invariant holds. The set of valid paths is closed under the references relation. So all the paths in the valid thing have to exist in the references relation. No path in the references relation can be invalid. The references graph is also maintained in the opposite direction. Nix maintains a mapping refers path to set of paths that defines transpose of the graph defined by the reference. Now, I assume this is just for speed purposes. Doesn't strictly need to be there, but it is there such that people can make queries against the referrers. All right. Well, I think that's all I have time for tonight, folks. And stay safe out there, and thanks for watching.